Welcome back, everyone. Ready for another deep dive? Today, we're tackling the Ponzo illusion. You know, the one with those converging lines that make things look bigger or smaller?
Yeah, it's a classic.
We've got some really cool research to dig into from folks like Robert Patterson and Robert Fox, William Prinzmetal, Arthur Shimomura, Michelle Mikulinski, even Philip Schmidt and Anke Haberkamp. It's a familiar illusion, but we're going to go beyond just seeing it.
Right, we're going to understand why it works.
Exactly.
Hmm.
So, for anyone who might need a refresher, what exactly is the Ponzo illusion? What are we looking at here?
Okay, imagine this. You've got two parallel lines, same length, placed against a background of, like, converging lines, kind of like those classic railroad tracks disappearing into the distance.
Gotcha. So it's not just the lines themselves, it's how they're laid out in space.
Exactly, and that's the whole trick. Even though those parallel lines are identical in length, the top one, the one closer to where those converging lines meet, it always looks longer. Our brains are messing with us.
It's like your brain's convinced that top line is farther away because it's nestled between those converging lines. Right. And so to make up for that distance, it makes the line look longer.
That's the classic explanation, a depth cue messing with our perception.
And for a long time, a lot of scientists thought, okay, that's it, case closed.
Right, but there's a twist.
Oh, there's got to be more to it. Tell me.
So back in 1983, Patterson and Fox, they did this really neat experiment using stereoscopic images, and they actually figured out how to manipulate the depth of those converging lines, making them appear either in front of or behind the parallel lines.
So they could control whether the railroad tracks looked closer to us or farther away than the lines we're comparing. I bet that changed things up a bit.
It did. They found something called the front effect. The illusion, it got stronger when the converging lines appeared in front of the parallel lines, almost like those closer lines were having a bigger impact on how we see things.
It makes you think about like how we're wired to pay attention to things that are closer to us.
Right.
Maybe because they're more, I don't know, important for survival.
Yeah, and it suggests that this front effect could be tied to these deeper principles of like visual processing, how our brains filter and prioritize information.
My brain's already doing gymnastics over here.
Yeah.
But you said depth might not be the only thing going on, right?
Yeah.
What else could be happening?
Let's jump ahead to 2001. Prinzmetal, Shimomura, and Mikulinski, they threw a curveball with something called the tilt constancy theory. They said, hey, maybe the Ponzo illusion isn't so much about depth, but about how we perceive orientation.
Orientation. You mean like how we figure out if a line's tilted or straight?
Exactly. They got this idea from something called the tilt induction effect. Basically, it shows how easy it is to mess with how we see a line's orientation just by changing the lines around it.
I need an example. I need a visual.
Okay, picture this. You have a perfectly vertical line. Now, surround it with lines that are just slightly tilted. You won't believe this, but that vertical line will start to look tilted in the opposite direction. It's like those tilted lines are warping your sense of what's straight.
Okay, wow. So are you saying those converging lines in the Ponzo illusion, they're doing something similar to those parallel lines?
That's the heart of their theory. Those converging lines, they might be creating a kind of tilt induction effect, subtly warping our perception of whether the parallel lines are actually straight. And that influences how we judge their length.
So instead of those converging lines making us think about depth, they're messing with our perception of whether those other lines are perfectly straight, and that changes how long they look.
Exactly. They create this context that distorts our perception, and boom, the illusion happens.
Mind blown. Wait, didn't they also compare the Ponzo to other illusions to see if this tilt constancy theory held up? Like, they didn't just look at Ponzo, right?
Right. They looked at the Zollner illusion, where parallel lines look tilted because of those intersecting lines, and the Poggendorf illusion, where a line seems to shift when it passes behind a rectangle, all these classics.
And they all had this tilt thing going on. Like, was there a pattern?
What's fascinating is how consistent it was. The angle and orientation of those lines, it kept popping up. It really strengthens the argument for the tilt constancy theory.
So now we've got two major theories going head-to-head. The classic depth cue explanation, and this super intriguing tilt constancy theory. But it feels like we've just scratched the surface here.
We have. Now, what if we throw the idea of time into the mix? How long does it actually take for our brains to fall for this illusion?
Oh, now we're getting into the nitty-gritty of how our brains work. I'm all ears.
So in 2011, Schmidt and Haberkamp, they tackled this question head-on. They used this really cool technique called response priming paradigm. Basically, they could measure how long it takes for the Ponzo illusion to develop in our brains.
I got to ask, how do you measure something that happens so quickly?
Think of it like this. They flashed a super quick prime image of the Ponzo illusion, followed by a target image. And by measuring how people reacted to that target image, they could figure out how long the illusion was hanging around in their minds.
Right, so if the illusion was processed really fast, the prime image would have a big impact on how people reacted.
Mm,
But if it took a while, it wouldn't be as influential.
exactly. And what they found was the Ponzo illusion, it's not instantaneous. It takes time.
So I'm not fooled right away. My brain actually takes a moment to be like, whoa, that line's longer.
They found that the longer the delay between those images or the slower someone reacted, the stronger the illusion became.
That's like the more my brain stares at it, the more convinced it gets.
It really shows how our brains are actively working, making calculations, building our visual reality, and sometimes those calculations, well, they lead to illusion.
We've gone from simple depth cues to the complexities of tilt constancy, and now we're talking about the actual time it takes for our brains to be fooled.
And we've just scratched the surface. There are even more theories about the Ponzo illusion, each one adding another piece to the puzzle.
This deep dive is about to get even deeper, folks. Buckle up.
It really is amazing, right? How even an illusion like this shows how our brains are always working. We're not just, passively taking in information. We're constantly processing, interpreting, and sometimes, well, creating our own reality.
It is humbling, kind of makes you think. We think we're seeing the world as it is, but really our brains are back there making all these judgments, calculations, a whole 9 yards.
Absolutely. And the Ponzo, it's a perfect example of how those judgments can be so deceptive, but in a fascinating way, of course.
Okay, so we've got depth cues, the tilt theory. We even talked about how long it takes for our brains to be tricked. But I know there are even more theories out there. What other explanations have researchers looked at?
Well, some suggest that our brains might be, like, applying 3D rules even when we're looking at a flat 2D image.
So even though it's just lines on a page, our brains are trying to see it as if it's a real scene with depth and all that.
Exactly. Like, we're so used to a 3D world, our brains just can't help but apply those rules even when they don't quite fit.
Fascinating. It's like our brains are always on the lookout for patterns, trying to make sense of things.
Right. And one of these theories, it's called the low-pass filter theory. It suggests that our brains, they kind of prioritize low spatial frequencies when processing visual information.
Okay, gotta stop you there for a sec.
Oh,
Low spatial frequencies.
yeah.
Layman's terms, please.
Think of the blurring a photograph. You remove the fine details, right? And what's left are the basic shapes, the contours. That's your low frequency information.
Okay, I'm with you. So is this theory saying the Ponzo illusion happens because our brains are focused on those big picture shapes made by those converging lines, and somehow that messes with how we see the other lines?
That's the gist of it. It's like that low frequency information from those converging lines, it spills over onto those parallel lines and boom, distorted perception.
Interesting. But did they actually find any evidence for this? Did they test it out?
Oh, yeah. They compared the standard Ponzo illusion, the one with those long converging lines, to a modified version called the rectilinear version.
All right, gotta paint me a picture here. What's this rectilinear version look like?
Imagine the converging lines cut short. They don't go all the way to the parallel lines, they create gaps. So instead of that continuous flow, it's more like a frame.
Gotcha. So the converging lines are still there, but they're not, like, directly touching those parallel lines. So if this low frequency theory is right, it shouldn't matter. It's all about the overall pattern.
Exactly. Both versions should be equally trippy. But here's the thing. The illusion actually got weaker in that rectilinear version.
Wait, so those gaps actually made a difference. So much for the low frequency theory then.
Well, it definitely throws a wrench in the idea that it's all about those low frequencies. There's got to be something more going on.
Okay, one theory down. What other explanations did they explore?
Another one is the assimilation theory, which it's kind of tied to that famous Miller-Lyer illusion.
Oh, yeah, with the lines and the arrowheads. Are we saying the converging lines in the Ponzo are kind of like those arrowheads?
Oh,
Pulling our perception in one way or the other?
that's what the assimilation theory is all about. You know how those arrowheads can make lines look longer or shorter? It's proposing those converging lines might be doing something similar.
I get it. But how did they test that? Did they, like, add arrowheads to the Ponzo?
Not quite, but they did make a modified version that kind of borrowed from the Miller-Lyer. Instead of being straight, the converging lines, they had these little wings at the ends, mimicking those arrowheads.
They gave the lines little costumes. Did it work? Did it make the illusion stronger?
You'd think so, right? But actually, no. It actually made it weaker.
That's weird. Adding those Miller-Lyer elements actually made the illusion less effective. What's that tell us?
It might mean that the Ponzo and the Miller-Lyer illusions, They're not as closely related as we thought. They might tap into different things going on in our brains.
Okay, so we've ruled out the low-pass filter theory, the assimilation theory. Are there any theories left standing in this battle of the illusions?
Well, there's one more big one, and it's probably the most intuitive, the perspective theory.
Okay, so this is all about how things look smaller the farther away they are, right?
Yeah.
Like those classic drawings of roads disappearing into the
Well,
horizon.
exactly. The perspective theory, it basically says we see those converging lines as a depth cue, kind of like the converging lines in a landscape painting.
So our brains are looking at those lines and thinking 3D scene, even though it's flat. And because that top line is closer to where the lines meet, our brains think, oh, it must be farther away, so it must be bigger.
You got it. That's the perspective theory in a nutshell. It's a good explanation, but the researchers wanted to be sure.
Makes sense, but how do you test just the perspective part when there are all these other things going on, like orientation and all that?
They did a clever experiment with 3 different versions of the Ponzo, each one designed to test a specific theory.
3 versions. Okay, I'm hooked. What were they?
So the first version was the classic Ponzo, our control group. The second version, it was designed to test the tilt constancy theory. They offset the parallel lines, so they weren't directly across from each other. One was kind of shifted to the left, the other to the right.
They were staggered. Why did they do that? How does that relate to tilt constancy?
Remember, tilt constancy is all about how surrounding lines can mess with our perception. So by offsetting those lines, the converging lines would affect each one differently, maybe weakening the illusion. If the theory holds up, that is.
Did it work? Did it weaken the illusion?
It did. The illusion was weaker in that offset version. 1 point for tilt constancy.
All right, score 1 for tilt. What about the third version? How did they test the perspective theory?
For this one, they got rid of one of the converging lines. It just had one line going up. The idea was if perspective is all it takes, even with one line, we should still see the illusion.
It's like they took away one of the railroad tracks. But wouldn't our brains still kind of fill in the missing track?
Yeah.
And wouldn't we still see the illusion?
That's what you'd expect if perspective's the key. But guess what? With just one line, almost no illusion.
Wow, so even with that depth cue there, it didn't really work. Does that mean perspective's totally out the window?
It at least suggests that perspective on its own isn't enough. It might play a role, but it's not the whole story.
Okay, so we've looked at low-pass filter, assimilation, and perspective. Tilt constancy seems to be the winner so far, but I'm still a bit confused.
What's tripping you up?
If the Ponzo isn't just about depth, then why do all these explanations involve, like, 3D thinking? Why are our brains so quick to jump to that?
That's a great question. It shows how deeply wired we are for 3D perception. Think about it. We've evolved to live in a 3D world. So our brains are always on the lookout for cues about depth and distance.
So even when it's a flat image, our brains are still trying to see it as 3D.
Exactly. And sometimes those mechanisms, they lead to illusions. The Ponzo, it's a perfect example of how powerful those 3D processing mechanisms are.
It's like our brains are so used to 3D, they just can't help but see depth and perspective, even when it's not really there.
Exactly. It shows that what we see, it's not just what's out there, it's our brains actively constructing reality.
This has been amazing. We've looked at the Ponzo from every angle, depth cues, tilt constancy, time, the whole shebang.
And it all points to how active our brains are in creating our visual experience.
But we're not done yet. We've talked about behavior and perception, but what about the actual nuts and bolts of the brain? What's happening at the neuron level?
Now we're talking. Time to zoom in on the brain itself and see what's going on when those neurons meet the Ponzo illusion.
Okay, so now we're going even deeper, like into the brain itself. It's kind of wild to think we can actually see what's happening in there when we experience an illusion.
I know, right? It's incredible. We're not just talking about what we see, but what's happening in the brain that makes us see it that way.
I'm trying to picture those tiny little neurons firing away, creating this whole visual world in our heads. But how do scientists even measure that?
Well, one of the tools they use is fMRI, functional magnetic resonance imaging. It's pretty amazing. It basically lets us see which parts of the brain are working hardest during different tasks, like, looking at the Ponzo illusion.
So with fMRI, we can actually see the illusion like happening in the brain.
You could say that. Researchers have found some pretty interesting patterns, especially in the visual cortex.
Makes sense, right? The visual cortex, that's like the brain's command center for all things visual.
Exactly. It's where the brain starts to decode what our eyes are seeing. And there's this one area within the visual cortex called V1 that seems to be especially important for the Ponzo illusion.
V1, okay. What's so special about this V1?
Well, think of V1 as a first stop for visual information. It's where the brain starts picking out those basic features like edges, lines, and you guessed it, orientation. And here's the cool part. Even at this early stage, we see differences in activity depending on which line in the illusion you're looking at.
So even though the lines are physically the same, V1's already reacting differently.
Yeah, those neurons that represent the top line, the one that looks longer, they're more active than the neurons for the bottom line. It's like the illusion's already starting to form right there in V1.
Wow. So even before the brain fully processed everything, it's already making judgments about length.
It just shows how the brain's not just sitting there passively, taking notes. It's actively interpreting, analyzing, even making predictions before it has all the information.
So V1's busy doing its thing, but are there other parts of the brain involved? I mean, it can't be just one little area, right?
Of course not. The brain's a team player. We also see activity in areas like the parietal cortex, which is all about spatial processing and attention.
So it really is a whole brain experience, all these different parts working together to create the illusion.
Exactly. And that's what makes illusions so valuable for research. By studying them, we can learn how these different brain areas communicate and work together to create our visual reality.
It's mind-blowing that a few lines on a page can tell us so much about how our brains work.
It's true. Illusions are like a window into the brain.
This has been an awesome journey. We've gone from those basic converging lines to depth cues, tilt constancy, even the time it takes for our brains to be tricked. And now, the actual activity of those neurons?
And you know what? We've just scratched the surface. There's so much more to learn about the Ponzo and how our brains create the world we see.
It makes you realize how much is happening under the hood.
Yeah.
All the things our brains are doing constantly to make sense of the world.
And illusions, they remind us that our perception, it's not just about what's out there. It's about how our brains interpret it. It's a collaboration.
So next time you see an illusion, don't just think of it as a trick. Think about all the amazing things your brain is doing to create that experience.
It's a reminder of the power of our brains, always working to make sense of the world, even when it's a bit, well, illusory.
Well said. And on that note, it's time for us to wrap up this deep dive. We've covered a ton, and I hope this has sparked some curiosity for you all.
Absolutely. Until next time, keep exploring, keep questioning, because there's always something new to discover about how we perceive the world.
Thanks for joining us.